Hi students, in the last video we discussed about event, what is sample space and what are different types of events and what are different types of sample spaces. Now I would like to discuss about mutually exclusive event. So this is very important term in probability, mutually exclusive event. So now I am considering one experiment. The experiment name is tossing two coins. So in this experiment, I am taking two events, event A and event B. Two events I am taking, and event A is having output as head only, head as an output, and event B is tail as an output. So in this experiment tossing two coins, the sample space consisting of the total outcomes as, so the possible outcomes are head and tail, tail and head, and tail and tail. So we have only four possible outcomes in this experiments. And coming to event A outputs, so whenever you consider event A, so what is the event A? Head as an output. So what are possible outcomes? So head tail and tail head. So these are the possible outcomes to be considered as an outputs for event A. So I'm writing all these things here. And event B is the tail is only output. So what are the outcomes? So this one, and this one. So I can write head, tail, head, and tail, tail. So now if I would like to get an event that exactly one head and one tail, so now I am considering an event, so which consists of one head, one tail. So now I can take A intersection of B, A intersection of B. So what are the common terms in the two? So whenever you observe the outcomes of event A and event B, so the event is consisting of one head and one tail. So this one head and one tail, and one head and tail, and from this the two, so these are the two. So the common points and the required outputs are one head, one tail, and the same tail, head. So that means from event A and event B, if you consider, you have common outcomes as head, tail, and tail, head. So you have outcome for this common element. Now I am taking one more example. So tossing two dice. So in this experiment, I am considering one event A. So in this event A, the sum of the outcomes from the two dice is 7. If you perform tossing two dice, the outcome of dice 1 and outcome of dice 2 is considered. So if it is x and this is y, so x plus y is equal to 7. This is the event, and I am taking event B as the sum is equal to 6. Okay, now let us take the possible outcomes for event A. So I am tossing two dice. So let it be the first output from dice 1 as 1 and dice 2 as 6. So the possible outcome is 7. The total sum is 7. So it is considered as one outcome. Similarly, 2 comma 5 and 3 comma 4, 4 comma 3, 5 comma 2, 6 comma 1. So these are the possible outcomes for event A. And now for event B, the sum of the outcomes of the two D1 and D2 must be 6. So the possible outcomes are, what are the outcomes? 1 comma 5, 2 comma 4, 3 comma 3, 4 comma 2, 5 comma 1. So these are the outcomes for event B. Okay, so now from event A and event B, try to find out the common terms A intersection B. Is there any element from this A and B? So there are no common elements. So this is a null set which is represented as 5. A intersection B is equal to 5. So if you observe the two examples, in this case we have two possible outcomes for the intersection, and here for the intersection there is no possible outcomes and it is considered as null set which is represented by 5. So this case where there are no common outputs between two elements, between two events, then the two events are called mutually exclusive. The events are called mutually exclusive elements. So this is not valid. This case is not valid, but this case is valid. So whenever you have no outcomes, common outcomes between two events, so then the two events are said to be mutually exclusive events. So now we will take axioms of the probability. So now to explain the axioms, I am taking event A as an event, and its probability is represented by P of A. And the corresponding axioms are given as the first one. So in some textbooks, simply they can write as probability of A is greater than or equal to 0, or you can also represent as 0 less than or equal to probability of A less than or equal to 1. So because that means probability means assigning non-negative number for the existence of one event. Okay, so the event may exist or may not exist. If exist, it can be 1. If not exist, it can be 0. If intermediate, that is uncertainty, then the value is going to be like that, between 0 to 1. So that means you have to take only non-negative number. And axiom 2. Axiom 2 is probability of S is equal to 1. So generally, whenever you take any experiment, it's going to have some events, and events will have outcomes. So all the outcomes are going to be in sample space only. So one sample space for one experiment. So universe is itself one sample space, one event. So that's why the set S is simply called as an event, and its probability is 1, because in the universe we are going to have different number of events. In the universe we are going to have different events, and for every event we are going to have one output. So simply S is an event and its probability of occurrence is always 1. There must be one outcome for an event in the universe. Okay, so this is also called as certain event because its probability is always 1. So this is called certain event. This is called certain event. And there is another event which is called as impossible event, which is called as impossible event. So impossible event means the event where you don't have outcome. That means simply saying a null set. in the previous example we have taken one event, there is no any outcome between A and B, so that is simply taken as null set. So simply I can take this as probability of pi is equal to 0. So this is impossible. If probability of any event is equal to 0, that means you can take this as impossible event. If probability of any event is equal to 1, that is called certain event. Okay, and coming to the third one, third axiom. So in this axiom, you can consider a sequence of mutually exclusive events. So I am taking sequence of mutually exclusive events starting from A1, A2, so on. Okay, and mutually, since they all are mutually exclusive, I can take the condition as AI intersection AJ is equal to phi, where I is not equal to J. So for this condition, probability of union of I is equal to 1 to infinity, probability AI is equal to sigma I is equal to 1 to infinity probability of AI. So simply saying, if there are multiple number of mutually exclusive events, the probability of union of all the events is equal to summation of individual probabilities of the corresponding events. So that is, and let us discuss in detail about this last exam. So these are the three exams only, and let us discuss the three exams. So now I am taking that a sequence of events A1, A2, A3 and so on. And here I am assuming that A1 is equal to S and AI is equal to phi for I greater than 1. For I greater than 1. And all the events are mutually exclusive events. Okay. And sample space S is equal to all the events. So simply I can write this as S is equal to I is equal to 1 to infinity AI. So as per the exam 3, probability of S is equal to sigma I is equal to 1 to infinity probability of AI as per the exam 3. Okay, and I am trying to expand this. So here I is equal to 1. So this one is going to be probability of A1 plus sigma I is equal to 2 to infinity probability of AI. Okay, and here probability of A1. So this is A1 is initially we have taken A1 is equal to S. So I can write this as probability of S plus sigma I is equal to 2 to infinity probability of AI. AI is considered as pi only, null set. So probability of pi. So from this expression, I can write probability of S is equal to probability of S plus sigma I is equal to 1 to infinity, sigma I is equal to 2 to infinity probability of pi. So the 2 gets cancelled and sigma I to infinity probability of pi is equal to 0, or you can also write this as probability of pi is equal to 0. That means the existence of null set is always 0. That means there is no possibility to occur. You can also state this as the occurrence of the null set will have the probability that is equal to 0 occurrence. Okay, so this is for infinite sequence. I is equal to 1 to infinity or 1 to 2 to infinity something else. Now you can consider a finite sequence. So finite sequence means you can have A1, A2, A3, so on, AN. So for this case, the final exam 3 is represented as I is equal to 1 to N AI is equal to sigma I is equal to 1 to N probability of AI. So this is exam 3.